All right, we are going to use that new theorem, SSS, or side, 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 to prove that triangles are congruent. So I said a second ago, or if you just got done watching the foldable video, we are still, back to that last section, we are still functioning under the definition that if two triangles are congruent, all their corresponding parts are equal. What we're talking about today is if I can get the corresponding sides in one triangle congruent to the corresponding sides in another, there's no possible way to construct a triangle where the corresponding angles are not congruent. So there's no need to go through the time and effort of showing that, because this will always happen. So what we're trying to do today is I'm trying to have you notice, can we use side, 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 or SSS to prove triangles are congruent? So we're not writing a complete two-column proof for every example. We are simply doing a lot of explaining because I want you to build to that ability to write a two-column proof with side, side, side. Okay, so number one, decide whether the congruent statement is true, explain your reasoning. So what I need to do is make sure, first of all, are these two triangles congruent, and is the order congruent? All right, so let's actually start with, are the two triangles congruent? So I'm going to go ahead and write out what I see is true, and then what other items I notice are true. So I've got AB congruent to CD here. So I'm going to write that out. I'm going to say segment AB is congruent to segment CD. And so these are things we would write in a proof. Okay, let's do the double tick marks. These two are congruent. So I see that segment AD is congruent to segment BC. Now, I want you to also notice that, I'm going to highlight this in red, this segment is the third side in this triangle over here, and the same segment is the third side in the other triangle. So here's what I want you to write down. I want you to write that segment BD is congruent. So I'm looking at segment BD on the triangle ADB is congruent to segment BD in the other one. Oh, I wrote C, I meant to write D. So I want you to recognize that this is the reflexive property of congruence. This unit, we will use this a lot. And the purpose of this property is to show that BD is actually in both triangles. So it's really two segments, but since it's a shared side, it's the same segment. So I want to also add here, I'm going to add reflexive, because not only are you supposed to notice what's given to you, and I would consider these tick marks given, you need to find things that are true based on what you know. So I see here, and I actually want you to do this. I want you to put 3 marks right here. Because here's what I want you to see. If I cover up this triangle, I want you to see 1 tick mark, 2 tick marks, 3 tick marks. And I want you to see the 1, 2, 3 on the other triangle as well. So that means what I see here, even though in our foldable these triangles are separated, when I visually see 1, 2, 3 tick marks, 1, 2, 3, I know I have SSS. So when it says here, decide whether the congruent statement is true, explain, I'm going to say yes by SSS, but let's check the ordering. So is AD congruent to CD? I'm sorry, AB. AB congruent to CD. So I've got AB and CD. The second and third, BD, DB. Well, that's my reflexive. How about the first and last, AD, CB? And I've got AD and CB right here. So yes, these triangles are congruent by SSS, and that ordering is correct. All right, let's look at number 2. Let's see if we can show the triangles are congruent. So I see 2 9s. So I see that XY, segment XY is congruent to segment ZY. I see 2 6s, so I'm going to put 2 marks and 2 marks. XW, segment XW is congruent to segment ZW. And there's a 4 here, but notice that you're reflexive. I'm going to add a triple mark there. So WY is congruent to segment WY, and I'm going to write reflexive here. So it looks like we have SSS, but are these in the right order? So is XW, the one with 6 over here, congruent to WZ, 6, yes. WY is my reflexive, ZY. Okay, so WY in the left triangle is not congruent to ZY in the right triangle. So I'm going to say here, I'm actually going to go like this. Decide whether the congruent statement is true. No congruence statement in wrong order, is in the wrong order. Congruence, and I'm just going to abbreviate statement, in wrong order. So yes, the triangles are congruent by side, 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 but the statement I'm provided with in this problem is not in the correct order. All right, I want you to try 3 and 4. So go ahead and pause this video, and I'd like you to give 3 and 4 a shot. Okay, I just went through here. This one's a little bit tricky in that you have PQ and TR with single marks, but then P down to R they have single marks, but it'd be like saying if this one is 5 and this one is 5, the whole thing is 10, and then you'd have the same thing here, 5 and 5 is 10. So that's why PR goes with SR. So let's just check the order. PQ, TR, QR, TS, P to R, S to R. Okay, so number 3 looks good. It is congruent, SSS. The statement is in the right order. Okay, number 4, let's see. I see 2, oops, I didn't mean to do that. I see a 4 and a 4. So I see that segment KN is congruent to segment PN. Okay, I'm looking here at 6 and 5. So I'm actually going to stop right here. Those are not congruent. And then I also see the other way I could verify this. So from M to L, you could argue that that is a reflexive. But the rest of it in the top triangle is 2. But the rest is 1. So that is not going to be the same length either. So I'm going to say not congruent. And then I might just list out that segment JK is congruent. I'm going to put a slash through it for not to segment PN. Okay, so if I don't get my sides to align, then clearly they would not be considered congruent. Okay, let's move on to the last couple. Okay, this next example, I don't have a number on it, says use the SSS congruence postulate, side, 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 to show that triangle ABC is congruent to CDE. So in order to do that, I need to show the sides are equal. Okay, I need to show that AB is congruent to CD. I need to show that BC is congruent to DE, and then I need to show that A over to C is congruent to C over to E. So when I look at this picture, I need to figure out, well, how do I find the length of those segments? You're going to use distance formula. I also want to show you Pythagorean theorem because some of you might be thinking, or when you've learned Pythagorean theorem, we could use that on this. Now, we haven't talked about Pythagorean theorem in geometry yet. We will get to it later in the unit. So I would stick with distance formula if you're not comfortable with Pythagorean theorem. Okay, I'm going to start with segment AB. Now, distance formula is going to be x2 minus x1 squared plus y2 minus y1 squared. So if I'm looking at A down to B, I am going to have to plug in those coordinates. So I might start, I'll say B is x2. So I'm going to say negative 3 minus 2 squared, y2 minus y1. I guess I did that backwards. I put this one first. Since you're adding these together, it doesn't matter the order here. Since I already wrote that, I'm going to continue with the x's. But I probably, since I wrote my formula here, I should have started with the x's. But I'll just continue in the same order. So I would have negative 3 minus negative 4 squared. Okay. Negative 3 minus 2 is a negative 5. This is going to actually be plus. So negative 3 plus 4 is 1. So then I would have, I'll just kind of continue to the right. Negative 5 squared is 25. 1 squared is 1. So I'm getting the square root of 26. Now I am just going to leave it there. I don't need to simplify that down because my goal is to get the square root of 26 on the other segment. Okay. So let me show you how to do Pythagorean theorem on the other one. So we did AB, we're going to do CD. So Pythagorean theorem is a theorem that is used in right triangles. So you have an A length and a B length on the two sides that make the right angle, and the diagonal hypotenuse is C. And so we use the formula A squared plus B squared equals C squared. So I need to make a triangle here. So I need to draw on this and create a triangle. Okay, so CD is right here. So CD is going to be my hypotenuse. So I'm going to create the rest of the right triangle around it. So there's my right angle. So see how I drew a vertical and horizontal line to create, I'll call this side length A, side length B, and side length C. Now, what this does for me is vertical and horizontal lines, I can just count their lengths. So if I'm thinking about A squared, the length of A is 1, 2, 3, 4, 5 units long, 5 squared. The length of B is just 1 unit. And I don't know the length of C. I'll just leave that C squared. So now I can just solve this out. So 5 squared is 25. 1 squared is 1, C squared. 25 and 1 is 26. And when I solve for C squared, I need to take the square root of both sides. So I get the square root of 26, which matches what I have here. So Pythagorean theorem is really just, distance formula is just Pythagorean theorem rewritten with coordinates. So if you want to do Pythagorean theorem, you'll be drawing all over your picture to create the A and the B. It doesn't matter which one we call A and B. Or stick with distance formula. Okay? All right, I want you to try the next two. Check BC. Calculate the length of BC and calculate the length of, I guess BC goes with DE. Okay? And I'm going to do one distance and one Pythagorean theorem just to keep practicing it. Okay, pause and come up with these two lengths. You should get the same number because we're just trying to show that this is congruent. Okay, so pause it and work through this on your own. Okay, I'm getting square root of 13 here. DE, I'm going to make my right triangle around it. Okay, so I'm going to make 1, 2, this is 3 units long. The one's vertical is 1, 2 units. And then this is my C, so I'll call that C squared. So that's going to be 9 plus 4. Can you see that, how that's showing up in the under the radical? So I get 13. So the length is square root of 13. Okay? I'll go ahead and just continue on here with the last group, AC. So I'll do distance formula like I've been doing. All right, so that is going to be -1 minus -4. And then 0 minus 2. So that's going to really be plus. So -1 plus 4 is 3. -2. 9 plus -2 squared is 4. Looks like I'm getting square root of 13 again. Kind of a coincidence, I got the same thing here. And then I will go ahead and wrap up CE with Pythagorean theorem. Okay, so I need to make a right triangle around it. So I've got my, I'll call that A, oops, I'm off the screen here. I'll call that A squared and B. So this one is 1, 2, 3 units. 3 squared. 1, 2 units. And then I'm ultimately wanting to calculate the C value. So that's going to be 9 plus 4 equals C squared. And see how I'm getting the 9 plus 4 over here? Let me move this out of the way. So I'm getting that same 9 plus 4, so I'm getting 13, so square root of 13, okay? So what we're doing on this example is we are showing that the lengths are the same. So you can choose distance or Pythagorean theorem. I think eventually you'll lean towards Pythagorean theorem, especially on these types of problems, because if our diagonal line is going to be our C, then you can quickly get the A and the B. Okay, well, we have one more example. We're going to use SSS in a proof. So let's get our proof set up here. So I'd like you to go ahead and make your 2 columns. And we've got statements and reasons. And then I'm just going to go ahead and still put both givens in line 1. So segment DA is congruent to segment DG. And I'm going to go ahead and mark that with a tick mark. And then R is the midpoint of AG. And that is given. Okay, so we're going to start with our givens. Can't do a whole lot more with a segment congruent to a segment. But if R is the midpoint of AG, so point R is the midpoint of this whole segment, I can create a second line off of that. So what does the midpoint mean with respect to a whole segment? Well, it means that it cuts AG in half. So it means that the left side of the midpoint is congruent to the segment on the right side. So it means that AR is congruent to GR, and the reasoning for that is that's just what the definition of midpoint is. So we'll write definition of midpoint. So I've got segment AR is congruent to segment GR, and that is by definition of midpoint. Now let's look at what we're proving, and we probably should have done this at the very beginning. We're proving triangle DRA, the triangle on the left, is congruent to triangle DRG, the triangle on the right. All right? So we're going to use SSS here because I want you to see how this works in a proof. So I almost have it ready. I only have one more side, and I have a reflexive. DR is in the triangle on the left, DR is in the triangle on the right. So this is my reflexive segment. So I'm going to put 3 tick marks because I've already used 1 and 2. Line 3 is going to be segment DR is congruent to segment DR, and that is our reflexive property of congruence. Reflexive, I usually shorten property of, and then I would use the congruent symbol. And so I now have shown side, side, side. So I'm ready to do step 4. I'm going to copy this statement down. Triangle DRA is congruent to triangle DRG, and my reasoning is SSS. So this is kind of what a typical proof would look like. We're going to add a whole lot more reasons here off our foldable, and I think you'll find as we do proofs this unit, it'll start to come together and not be quite as, I guess, quite as difficult as they have been.